A theory of everything, often referred to final theory, ultimate theory, or unified field theory, is a hypothetical, singular, all-encompassing, coherent theoretical framework of physics that fully explains and links together all aspects of the universe. Finding a theory of everything is one of the major unsolved problems in physics. Over the past few centuries, two theoretical frameworks have been developed that, together, most closely resemble a theory of everything. These two theories upon which all modern physics rests are general relativity and quantum mechanics. General relativity is a theoretical framework that only focuses on gravity for understanding the universe in regions of both large scale and high mass. Planets, stars, galaxies, clusters of galaxies, etc. On the other hand, quantum mechanics is a theoretical framework that focuses primarily on three non-gravitational forces for understanding the universe in regions of both very small scale and low mass: subatomic particles, atoms, and molecules. Quantum mechanics successfully implemented the standard model that describes the three non-gravitational forces: strong nuclear, weak nuclear, and electromagnetic force, as well as all observed elementary particles. General relativity and quantum mechanics have been repeatedly validated in their separate fields of relevance. Since the usual domains of applicability of general relativity and quantum mechanics are so different, most situations require that only one of the two theories be used. The two theories are considered incompatible in regions of extremely small scale, the Planck scale, such as those that exist within a black hole or during the beginning stages of the universe, the moment immediately following the Big Bang. A theory of everything may be defined as a comprehensive theory that, in principle, would be capable of describing all physical phenomena in the universe. In pursuit of this goal, quantum gravity has become one area of active research. One example is string theory, which evolved into a candidate for the theory of everything, but not without drawbacks, most notably, its apparent lack of currently testable predictions and controversy. According to string theory, every particle in the universe, at its most ultra-microscopic level, the Planck length, consists of varying combinations of vibrating strings or strands with preferred patterns of vibration. String theory further claims that it is through these specific oscillatory patterns of strings that a particle of unique mass and force charge is created. That is to say, the electron is a type of string that vibrates one way, while the up quark is a type of string vibrating another way, and so forth. String theory, or M-theory, proposes 6 or 7 dimensions of spacetime in addition to the 4 common dimensions for a 10 or 11-dimensional spacetime. One remarkable property is M-theory, which is the requirement for 7 extra dimensions beyond the familiar 4 dimensions of space and time. This builds upon the Kaluza-Klein theory, which unified general relativity and electromagnetism by introducing a 5th dimension. In string theory, these extra dimensions are compactified, meaning they are small and curled up, adding layers of complexity to our understanding of the universe. Supersymmetry is another cornerstone of string theory, proposing a symmetry between bosons and fermions, potentially resolving the hierarchy problem of why gravity is significantly weaker than other forces. Extra dimensions allow gravity to propagate differently, providing a plausible explanation within the stringy framework. The theory also offers mechanisms to explain the hierarchical generations of fermions and their mixing rates. Unlike string theory, which posits the existence of tiny vibrating strings, loop quantum gravity focuses on the quantum properties of spacetime itself. Current research on loop quantum gravity may eventually play a fundamental role in a theory of everything, but that is not its primary aim. LQG introduces a lower bound on the possible length scales, suggesting that space is composed of discrete chunks rather than being continuous. Loop quantum gravity may not yet offer a complete theory of everything. Among these is the theory of Causal Fermion Systems. This approach seeks to unify general relativity and quantum field theory by treating both as limiting cases of a more fundamental theory. Here, space-time and matter are described by a single mathematical object, a causal fermion system. This theory offers a novel perspective on the quantum structure of space-time, yet much work remains to integrate it fully with the standard model. Next, we delve into the world of causal sets. This theory, like loop quantum gravity, proposes that spacetime is fundamentally discrete. However, it introduces a partial order to these discrete events, representing the causality relations between past and future events in spacetime. This unique approach aims to develop a working theory of quantum gravity, which might eventually include the standard model, becoming a candidate for a theory of everything. Lastly, we consider the intriguing ER equals EPR conjecture. This hypothesis suggests that entangled particles are connected by a wormhole, or Einstein-Rosen bridge. This idea links quantum entanglement with spacetime geometry, potentially providing a new pathway to unify quantum mechanics with general relativity. In parallel to the intense search for a theory of everything, one of the most compelling arguments comes from Gödel's incompleteness theorem. Informally stated, Gödel's theorem asserts that any formal theory sufficient to express elementary arithmetical facts and strong enough for them to be proved is either inconsistent or incomplete. This means there will always be true statements that cannot be derived within the formal theory. Stanley Jockey, in his 1966 book, The Relevance of Physics, pointed out that because a theory of everything will certainly be a consistent, non-trivial mathematical theory, it must be incomplete. He claims this dooms searches for a deterministic theory of everything. Freeman Dyson echoed this sentiment, stating that Gödel's theorem implies that pure mathematics is inexhaustible. Because of Gödel's theorem, physics is inexhaustible too. Stephen Hawking, originally a believer in the theory of everything, changed his mind after considering Gödel's theorem. He remarked, "Some people will be very disappointed if there is not an ultimate theory that can be formulated as a finite number of principles. I used to belong to that camp, but I have changed my mind." However, not all scholars agree. Jürgen Schmidhuber argued that Gödel's theorems are irrelevant for computable physics. In 2000, he explicitly constructed limit-computable deterministic universes whose pseudo-randomness based on undecidable Gödel-like halting problems is extremely hard to detect but does not prevent formal theories of everything describable by very few bits of information. Some physicists believe that the series of approximations in physics will never terminate in the truth. Einstein himself expressed this view on occasions. There is also a philosophical debate within the physics community about whether a theory of everything deserves to be called the fundamental law of the universe. Advocates of emergent laws, which govern the behavior of complex systems, argue that these laws are as fundamental as a theory of everything. Steven Weinberg pointed out the impossibility of calculating the precise motion of an actual projectile in the Earth's atmosphere, questioning how we can know we have an adequate theory for describing such complex phenomena. He suggests that a theory of everything must work for a wide range of simple examples in such a way that we can be reasonably confident it will work for every situation in physics. Difficulties in creating a theory of everything often begin to appear when combining quantum mechanics with the theory of general relativity, as the equations of quantum mechanics begin to falter when the force of gravity is applied to them. In conclusion, the quest for a unified theory of everything continues to captivate the minds of physicists and philosophers alike. While string theory and loop quantum gravity offer promising paths, the journey is far from over and the universe is vast, so keep seeking guidance.